Welcome to my circular motion playlist. Been talking about motion of a body in a circular path for some time now, as referring to my previous video lessons where I introduced circular motion, also define some terms that is used in what we call the kinematics of circular motion. And an example of such terms is angular velocity, angular acceleration, and then the relationship between angular speed and velocity. Now we move further to look at this topic still under circular motion in this presentation, radius of curvature, because when the body is projected, like in case of a projectile, whether it is horizontal projectile or projected with an angle theta degrees to the horizontal, this body describes a curve, a path that is circular or like a parabola. We need to be able to write down an expression for the radius of the curve at any point in time. So let's take, for example, of course, you see that the radius of curvature is defined as the square of the speed of the body at that point over the component of the body's acceleration perpendicular to the direction of motion, direction of the speed. So this is the basic definition of radius of curvature. Now let's see this example. A body is projected with an initial velocity u at an angle theta degrees to the horizontal. And I'm trying to draw here the variation of the body's vertical displacement against its horizontal displacement. And the u is of course, is a vector quantity, and here it is directed angle theta degrees with the horizontal. And of course, you know that this body is going to follow a parabola, a path that is curved like this until it strikes the ground at the same point in the same plane as the plane of projection. Okay, let's call this point O. That's the point from which this body is projected and then hits the ground again at point Q. Let's say the body rises to its highest point P here. Now, for these 3 points, we want to write down expressions for the radius of curvature because this looks like a curve. Of course, it's a curve. Can complete the path like this. This is another curve, and this point too. So, we are going to make use of the definition. How do we apply that to try to write down the expression for the radius of curvature? Okay, let me start with point O. I want to find the radius of curvature of the body at point O. That's the point of projection. So the velocity of projection is u. That's the initial velocity. I must look for, of course, we're going to take the square of this in this equation. That replaces our v squared or speed square. That's my u. Then I need to find the component of the body's acceleration. Remember, the acceleration acting on this body is called acceleration due to gravity, which acts vertically downward, g. Okay, but I need the component of this g perpendicular to the direction of motion. That is something like this. Okay, if I'm going to place a line here such that this line is at right angles to this direction of u. Okay, so this is the component I need. How do I find that component? Probably by a similar triangle. This is also my theta degrees because I can do something like this and also something like this to complete two right angle triangles which are similar. Consider this side is adjacent side, the same as this side is same as this, and this is same as this. So which means that if I resolve my G, I can resolve it into this component that is acting in line with the direction of motion, parallel or anti-parallel to the direction of motion. That is this component. If I resolve this my G, that gives me G sin theta. This is by using SOHCAHTOA. Opposite over hypotenuse gives me a G sin theta, which is also G sin theta here. Then I resolve for the component perpendicular to the direction of motion. That's going to be adjacent to hypotenuse. That is G cos theta. So that the radius of curvature, let's call that R1, at point O will be given by u squared, the square of the speed at point O, which is the initial velocity, over the component of that speed, which is g cos theta. Okay, that's the component of the speed that is perpendicular, component of the acceleration perpendicular to the direction of the speed. Okay, let's come to point P, the highest point reached by the projectile. Now, let's say, for instance, before then, that the initial velocity is 20 meters per second given, and that the angle of projection is 30. We can calculate quickly the radius of curvature at point O, which is 20 squared over g cos theta, that is 10 cos 30. If you have your calculator, they can evaluate that. That gives you 400, that is 20 squared, divided by 10 times cos 30, 0.866. That will give you 400 divided by 8.66. So you can calculate that and bring out the final answer. All right, quickly, let's look at the radius of curvature at point P. Okay, at point P, you need to understand that this body has two velocities. That is, its total velocity is resolved into two different components because a projectile motion is a motion of a body in two perpendicular components. So we have that the u component, that is the Vx component, that one is acting horizontally. We also have the Vy component, okay? But one thing about this motion is that at the highest point, the Vy component goes to zero. Just like when you project a body vertically upwards, on reaching its maximum height, the final velocity is taken as zero because the body is momentarily at rest before it starts falling back down. So at its highest point, the Vy component goes to zero. So that the resultant velocity is equal to the Vs component, okay? Because the resultant velocity at any point on the curve is supposed to be the square root of the sum of the squares of the two velocities, the Vy component squared and the Vx component squared. That's supposed to be the resultant velocity at any point on this path. Okay, so that will give you, since this is zero, that v becomes equal to vx, which is u cos what? Cos theta. Okay, now let's bear that in mind because we're going to make reference to it later. Now, the next thing is for us to find the component of the acceleration of the body at right angles to the direction of speed v or vx, and that component is just equal to the value of acceleration due to gravity, which is always acting vertically downwards at all points. So my g component that is perpendicular to the direction of speed is just g. So that the velocity or radius of curvature, we call that r2, at the highest point of the projectile is given as u cos theta all squared divided by g, which is our 10. So that gives me 20 cos 30 all squared divided by 10. Okay, I'm sure you are there with your calculator, so you can compute this for me quickly. That's 20 times cos 30 0.866, okay, divided by 10. Remember, you have to square this. So this times this should give me 17.3 squared divided by 10. So that gives me the radius of curvature at point P. You can use your calculator and complete that solution. All right, let's look at the last point, which is the point Q. Point Q happens to be the landing point of the projectile. You know, it falls for a while and then strikes the ground at point Q. Point Q is at on the same horizontal plane, a level horizontal surface as the point of projection. We want to find the radius of curvature of the body at point Q. Remember the radius, let's call that R3, is still given by the speed squared, the velocity squared at this point over the component of the G perpendicular to the direction of this. So for clarity, let me quickly redraw this diagram where I have enough space to show you how the parameters there are acting. So let's say this is still the graph of the vertical displacement against the horizontal displacement of the body. Okay, this is my u, this my angle theta, it goes like this and hits the ground here. Okay, so in this case, we're looking at point Q. Now, the body still has the horizontal velocity Vx, that is the horizontal component of its velocity is acting along this line, even at the landing point, and the vertical velocity Vy acts along this line. And recall that the acceleration due to gravity also acts along the same direction as the direction of Vy. So when we resolve the two velocities, Vy and Vx, we get our resultant velocity acting this way. Let's call resultant velocity V. And again, I told you earlier that to get our V, we need to use this expression, Pythagoras theorem, is Vy squared plus Vx squared. And the Vy component at this point, of course, that should give you u sine theta minus g times t. Okay, so but since we said that at the highest point, P, the Vy component is 0. So that when the body is here now, it's like it's starting to fall from rest from this point to this point. So we can take this as initial velocity for the vertical direction. This Vy is equal to 0 because initial. And what's the final velocity? That's the Vy component, the vertical velocity on reaching point Q. So that I can quickly use this equation, Vy equals u sine theta. This is 0 now. Okay, so that gives me g times t. All right, so but the time taken, what's the time of flight? Time of flight, given that this is 30 degrees, this is 20, we can quickly find the time of flight. Sorry, this is 20 meters per second. Time of flight is calculated using t equals 2u sine theta over g. You must have gone through my video on or gone through the topic projectile motion before you start dealing with this circular motion stuff. All right, so this gives me 2 times 20 sine 30 divided by 10. That is 40 sine 30 over 10. Okay, that gives me 2 seconds. That is the time of flight. 2 seconds when you evaluate this. Now, the 2 seconds is total time taken for a projectile to go from the point of projection, which is point O, to point Q where it strikes the ground. So, which means it will take 1 second to go from P to Q, since from P to Q is halfway of the journey from O to Q. So, it takes 1 second to go from O to P, and another 1 second to go from P to Q. Right? So, that's the 1 second I'm using there. So, I can find my Vy, which gives me what? 10 times 1, that is 10 meters per second. That's my Vy. And my Vs component remains u cos theta, which is 20 cos 30. That is 17.6 meters per second. All right, so that if I now want to evaluate my V, compute my V, that is the resultant velocity, this one now. That gives me Vy squared, which is 10 squared, plus, what is that again? 17.6 squared. Okay, this will also give me 20 meters per second at the landing point. It gives me 20. Okay, now I'm going to now use that to find the radius of curvature. But before then, I'll come back here. I need to find the component of this acceleration at right angles, perpendicular. I need to just place a line at right angles to the direction of the speed. So I need these components. Okay, so I place my theta here. Okay, this angle theta is the same thing as here. So I'm going to resolve this my acceleration g into this component, which is the sine component, opposite of hypotenuse, and the cosine component. So this component is the same thing because it's parallel and the same as this component. So this is my opposite over hypotenuse, that is g sine theta. So this g sine theta is a component of g that is at right angles to the speed. So that finally my radius of curvature R3 will be equal to v squared 20 squared over, what is that again, g sine 30. That gives me 400 over, hope you can still see my board that I'm writing down here. Okay, that's divided by 10 sine 30, which is 0.5. That gives me 400 over 5. That gives me what? The 80 meters. So that gives me the radius of curvature at the landing point of the projectile. Okay, the next video, I'm going to still solve 1 or 2 questions applying this equation of the radius of curvature. So please stay tuned, and I'll see you in the next video. Thank you.